Dev here. Today we're going to be solving longest mountain in array, LeetCode, medium question 845. And this question says that recall that an array is a mountain array if and only if it is an array of length greater than 3 and there is some subset of numbers in the array such that they are strictly increasing. As you can see, there's a less than, meaning that array of 1 is greater than array of 0, and array of I is greater than array of I minus 1, and then array of I is greater than array of I plus 1. And what that means is that there needs to be a subset in this array such that the numbers are increasing, such as 1, 4, 7, 3, 2, and then they are decreasing. So we have 1, 4, 7 are increasing, 3 and 2 are decreasing. Now it says that there needs to be both of these need to exist. So what that means is that just 1, 4, and 7 is not a mountain, and it does not count. There needs to be a decrease at the end of this mountain for it to count. So 1, 4, 7, 3, that would count as a mountain. That would be a mountain of 4 elements. But because there is also another element after the 3 that's a decrease, then we have 5 total elements, which is our output right here. And it says, and this can be confirmed by looking at this second example, it says that 222, which satisfies our constraint of it needing to be greater than 3 or equal to 3. 222 is not a mountain because all of the elements equal to each other. So what this tells us is that, let's say we were to have 1, 4, and then this 7 was another 4, that would not be a mountain. It's asking us to solve this using only one pass, and it's also asking us to do it without creating any auxiliary arrays or any additional arrays or anything like that. So first thing that we could possibly think about doing is to maybe have a double for loop and say, okay, starting at I is equal to 0 at our 2, we can then have another for loop inside there, counting maybe from I plus 1, which would be at the 1, and maybe counting, trying to find increases, and then have another loop that would find a decrease. But because we would have a for loop, because if we have an example of like a 4x in y and then a 4x in z type of loop, this is going to equate to a big O of n squared time complexity, and it's asking us to do this in one pass. So really what this is looking for is it's looking for a time complexity of linear time, which would be big O of n, where n is the number of elements in the array. And this can definitely be done. Actually, it's probably the more easy solution to do. And to kind of illustrate what I mean by they're looking for is, I have this this image here that I drew, and this is our array, our input array up here. And basically we have a graph, and this is kind of what it could look like. At an index 0, we are at 2. Index 1, we're at 1. Index 2, we're at 4. Then 7. Then 3. Then 2. Then 5. And we can see that we have a mountain happening right here, don't we? It goes up, and then it comes down. And then also right here, technically, we have the beginnings of another potential mountain, but because there's no decrease, we would need another decrease to make this a mountain. Because of that, this is not a mountain. Like this right here is not a mountain. However, because of those constraints being fulfilled, this is a mountain of 5. And the way that we can do this is, let's say we were to have 2 pointers, like a sliding window, and you put pointer 1 and pointer 2 is here, And then what happened is you would look at, or rather down here, we have 2 and then we have 1. Oops, 2 and 1. And we could say, is 1 less than 2, or is it greater than 2, or is it equal to 2? And so in this case, it is less than, 1 is less than 2, so it is a decrease. And so we would then set some sort of variable that's going to keep track of the previous, state of this this array. And so the state at this point would be decreasing, right? We would have a decrease. And so then we go from, or let me put the D over here. We have a decrease. And then we would go from a 1 to a 4. So basically we're sliding over a little bit as far as like our sliding window. So now we went from 2 and 1, now we're at 1 and 4. And this is an increase. And what we can do is now we could say that our mode is no longer a decrease, but we are now entering into an increasing mode. And if we are increasing, that means we have the potential, just like right here, we have the potential for a mountain to be forming. And then we will move over again. So from 4 to 7, it's also an increase. And so our mountain, our potential mountain, we call this potential mountain at this point, when it was at 1 and 4, was at 2. But now, because we're at 4 and 7, 7 is greater than 4, it's an increase. Our potential mountain is now 3. And then we would continue this. So we're at 7 and 3. Oh, this is a decrease. 7 is greater than 3. So that means that we are now at a decrease, but check this out. Because we're now entering a decrease, meaning we are right here. Because we're now in a decrease and previously we were in an increase, our potential mountain is going to get incremented. We are still in a mountain. We are now at 4, but the mode that we are in right now is that of a decrease. So we're now in a decrease, and we only set the mode as decreasing to keep track of a decrease if it was preceded by an increase. So for instance, if we had a graph that looked like this, and we had a couple points here that looked like this, and then went down and then down, this right here would technically is decreasing, but it wouldn't be considered a decrease as far as our state is concerned, because we only care about a decrease if it was followed by an increase, which, as you can see, there's a decrease here, but it matters to us because it was followed by an increase. And this will make more sense when we write it out in code. And then if we continue, we go from 3 to 2, and it is still decreasing, and now our potential mountain is at a 5. And then from 5 to 2, we're now increasing again, but because we're now increasing, so now the mode is no longer decreasing, we're now actually going to be in an increase, so we can set it back to that. And this is our potential mountain is our answer. And basically we would set, there could be more mountains if this was to continue on for more numbers in the array. There could be possibly more other mountains, so we would actually set maybe a longest mountain variable to 5, and that could be overridden potentially in any of these numbers in the array if they were to come in the future. So let's see if we can write a solution. So we said that we've been told that if the length of the array is less than 3, then we're going to return 0, which it says right here. Return 0 if there is no mountains, and there is no mountains if the whole entire array is less than 3. Can't we agree on that? And I said we need a couple of variables here. We need the current state, which could either be increasing, decreasing, or none. Decreasing or none. We need the longest mountain set equal to 0, and then we need the longest we need the current mountain. So set that equal to 0 as well. And at the very end here, we're going to return the longest mountain. And to actually accomplish what we're looking to accomplish here, meaning to start at this, up here at the top, to start with these first two numbers, we're going to start at this first index, and then we're going to look at the index prior to it. So basically we're going to start our for loop at the 1, and that's also index 1, and then we're going to say, is index 1 less than or equal to the array at index 1 minus 1, or rather, you know, the number prior to the current number of the index. Let me show you what I mean. So we're at 4I in range. We're going to start at 1, and we're going to go to the length of the array, like so. Okay. If you're unfamiliar, range is start, stop, and step. And it stops, it's exclusive. So it is inclusive at the start, meaning it will include a 1 in the range. It will not include the stop. So if the stop was 5, it would stop at 4, depending on what your step is. And the step is just the amount of numbers to increase each time you pass through this iteration, okay? And so we're going to say if the array at I minus 1 is greater than, we're going to have to count for all three, so if it's greater than the array at I, this means that the number prior to this current number was greater. That means we're in a decrease. Else, or if, the array at I minus 1 was less than the array at I, that means the number previous to this current number was lower. So it was, this number was less than this number, so it's now in an increase. So we're in an increase. And then else, that means they're equal. We're just going to set the current state is equal to none, because if they are equal to each other, then it's just a flat line. And likewise, right here, we don't care about flat lines. So actually, we do care about flat lines, because flat lines indicate that we are now no longer in a mountain, and we can set the current mountain equal to 0. And now what we want to do is we want to say if we're in an increase. So if we're increasing, and let me think here for a minute. If we are the array of the number previous to this number was less than this number, that means we are in an increase. That means we want to increment our current mountain pointer by 1. So first off, we're going to set the current state equal to an increase, and we're going to say if the current state is equal to increase, then we are going to add current mountain plus equals 1, else, meaning if we are in an increase, meaning the current state was already set to increase, we're going to add 1. This, if we're in this block, that means that we are at a point in our array where we are beginning to increase. We are right here. So the first time that this block right here is executed, meaning it is seeing an increase, meaning there was no increase prior to this, we're going to set the current mountain equal to 2. The reason why is because there's 2 numbers within our sliding window. I think that you can see that there's 1, 2, 1, 2, 1, 2. We're looking at 2 and 1, 4 and 1 and 4, 7 and 3, 3 and 2, 2 and 5. There's two numbers within inside of our sliding window, okay? And then we're going to be setting, so the first time, so basically it may even make more sense to say if it's not in an increase. So the first time that we see an increase but we're not in an increasing mode, then we're going to want to set the current mountain equal to 2. Otherwise, we have already been in an increasing mode. We want to just continue incrementing our current mountain by 1. Okay, hope that makes sense. Now let's say we're in a decrease. If we're in a decrease, obviously we're going to want to set our current mountain, our current state equal to a decrease. But we only care about, remember I said we only care about decreases, meaning we only care about this decrease if it was preceded by an increase. So because these were increasing prior to decreasing, then we care. So if we were to enter into this if block and the current state was increasing, then we would want to now enter into a decreasing, in quotes, a decreasing state. So if the current state is equal to increasing, now we want to say that we're decreasing. We want to set this to decreasing. Whoops. So we're increasing, and now we're kind of decreasing, but because we were increasing, now we're going to be decreasing. I hope this makes sense, but I think it does. That's good for that. Now, what happens if we're increasing and now we are decreasing? A decreasing state means that there was an increase and now we are decreasing. And so what we can do is we can add 1 to our current mountain. That means if we're in a decrease, that means we can add 1 to our current mountain, meaning we were at 1, 2, and then 3, 4, right? So we could say if current state is equal to a decrease, we can add 1 to our current mountain plus equals 1. Okay, but here's something we also need to account for. What about this state? What if we came from an increasing state? Well, if we came from an increasing state, that would also constitute an addition to another step being added to our current mountain. So we can also say, or current state is equal to increasing. So if current state is decreasing or it's increasing, we're going to add the current mountain is equal to plus equals 1. How do we set our longest mountain? Well, we said that, for instance, if we are, I'll change the color here to like a bright red. If we are increasing but stop, meaning we increase, I don't like that color. Let's do a beautiful blue. So if we are increasing but then we stop, meaning this is the end of our array, there's no mountain because there needs to be a decrease. So once we start decreasing, then we can be sure that there is a mountain. And what we're going to do here is we're going to set the longest mountain. It's going to be equal to the max of the longest mountain, meaning whatever the current longest mountain is, the max of that number, and whatever the current mountain is. This will ensure that, like I said before, maybe this mountain was 5, but then later on down the road there was another mountain that was 20. The longest mountain would be the max of these two mountains. And then we're going to return our longest mountain. The time complexity of this, let's just look at it together. So what we're doing is we're going to be traversing basically the entire length of the array subtracted by 1, which doesn't really matter. We always drop non-dominant terms in big O notation. So our time complexity would be big O of n time, where n equals of elements in an array, and then the space complexity is going to be a constant space. The reason why it's constant is because we are setting the current state, the longest mountain, and the current mountain, but that's only 3. So really you could say that, you know, it's 3, but in reality we're just going to put 1 space, and that will be it. Let's run through it. Let's test it really quick just in our heads to make sure that this runs. So we have, if the length of our array is less than 3, we're going to return 0. We have a current state is equal to none, longest mountain is equal to 0, current mountain is equal to 0. We're going to say the range from 1 to the length of the array. If the array at I minus 1 is greater than I, so this is where I would probably pay attention to so that I wouldn't have a bug. So we're saying that 10 is greater than 4. So that means we are decreasing, and let's just comment here, decreasing values. And then, okay, so that makes sense to me. And then we're going to be here, and so we would have, if it's less than, so 10 is less than 20, that means if we went from 10 to 20, we are increasing. So this is an increasing values. And so we said if the current state is decreasing or the current state is increasing, if we're coming from an increase, which is what this would be, then we want to add 1 to the current mountain and update our longest mountain, because we've now entered into the decreasing state of our mountain, and we want to set the current state to decreasing if it was previously increasing. And the reason why is because what if we had a function that was 4 2 1 0. Well, these would be decreasing and they would enter into this decreasing block, but we don't want, these are not mountains. This would look like this, and this is not a mountain. There's no initial peak. A mountain needs an initial peak, or rather an initial climb, if you will. So what would happen is if we didn't have this, then we would say, oh, 4 to 2, that's a decrease. So we want to add 1 to our current mountain. That's not the case. This protects us from saying if we are in a decrease but there was no climb, do nothing. Okay? And then our current state, obviously, if they're equal, that means we're at a plateau. A plateau is like this down here, where you go up and then you plateau and then you go down. That's not a mountain. We want a beautiful mountain. And let's run this code and see what we get. Awesome, it works. 19.37% faster than the other solutions, and almost half as less space as the other solutions. So I hope that helped you guys.